Welcome back to math. Today we are going to go over Unit 1. We're going to do a quick review of systems of equations in preparation for the finals for the semester. So our objective today is pretty much going over everything from Unit 1. Given a problem involving systems of linear equations, I can choose a method to solve and write the solutions with 75% accuracy in 4 problems. So take a look at those emojis there. Think about which one best represents you on this objective. So let's remind ourselves what a system of equations is. 2 equations in 2 variables that are solved together. So if you'll recall, they looked something like this. We'd get y equals 1/2 x plus 2, and this is just an example. Y equals negative 3x minus 1, and then we'd have curly braces around them like that. So that's what a system of equations looks like. And we had several ways to solve these. The first way we had was graphing. So we have graphed by hand many times in this class. We haven't done it in a while though, so maybe let's give it a quick look to remember how we graph slope-intercept form. So on this first one, we have mx plus b, right? Slope and intercept. Oops. Not plus 4, but plus b. That's our slope-intercept form, y equals mx plus b. So in this case, our slope is 3/1, and our y-intercept is negative 4 for that first one. So we go to our slope, or we go to our y-intercept, we make a dot there, negative 4. And then we use the slope to make our next dot. We go up 1, 2, 3, and right 1. And we get a dot there. We can continue going up if we want. 1 up 3, right 1. And all of those dots will form a line. And we can draw, whoops, that's not the correct line. We can draw that line through all of those dots. And that is going to be the graph of that line. So that's our graph of that first one, y equals 3x minus 4. There we go, kind of like that. Now we graph the second one pretty much the same way. Maybe I'll choose a different color though. The second one we'll do in, how about blue? So we're going to have a y-intercept of 7. And now we have a slope of negative 2/3. So that means we're going to go down 2, right 3. Down 1, 2, right 1, 2, 3 here. And again, we can continue doing that to make more points if we want to. And then we draw that line. Oh, it won't let me move that line. Here we go. We draw this line straight through all these points. So now we have both of those equations graphed. This is our, this is our first graph. This is our second graph. And where they intersect was going to be our solution. So you can see right there, it intersects at 0.35. So that is our answer here. 3, 5. And we write our answer as an ordered pair. Or we could also say x equals 3, y equals 5. Same difference. So, really quick overview of graphing. Remember how to graph slope-intercept form. And we can solve a system of 2 linear equations by graphing them and seeing where they intersect. Okay, now that we've gone through all that trouble, remember that you can use Desmos though. You can also just go out to Desmos. And you can just Google Desmos if you don't have the link, or I can put it in the video description. So if we're given this system of equations and asked what is the solution, we can just go over to Desmos, open that up, type in these equations, and this is the picture that we get. We see this picture, and we can look at this and ask, what is our solution here? Can we just see our solution? Sure we can. Yeah, it's right where they intersect. Our solution is 2, -4. Super easy if we just use Desmos, right? Okay, how about this one? Jog our memories a little bit. What happens if both the lines are over the top of each other? When we graph them, they graph the exact same line. This one has infinite solutions because every single one of these dots on this line satisfies both equations. And we could potentially just draw an infinite number of dots. They'd keep going that way, they'd keep going that way, and we could even draw infinitely many in between them. So that's why there are infinitely many solutions. Remember, this doesn't mean that all the solutions are solve this system. That's not true. All these up here do not. All of these down here do not. It's only the points on this line. So it's infinite solutions on one of these lines. Since they're the same line, it doesn't matter which one we write down, but it's infinite solutions on one of these lines. Okay, how about this example? What's the solution here? It looks like these two lines are parallel. They aren't going to cross. What's the solution? Well, we just said that the solution is where they cross, and these aren't going to cross, so it makes sense that this would be no solution, right? Remember, we can also tell that by the slope. If the slope is the same, but the y-intercept is different, so in this case the slope is -1/3, but the y-intercepts are different. Oh, and this shouldn't be a +1, this should be a -1. That's our y-intercept there. But our y-intercepts are different and our slopes are the same. That means these are parallel. They have the same rise and run, so they have the same exact steepness, but they cross the y-intercept in a different place, which tells us that they're just going to be exactly the same steepness forever. They're never going to get closer together or farther apart. So let's do a quick overview of what we just looked at. So this is our systems vocabulary. My video's in the way. Here we go. And what we're primarily looking at on this chart is the number of solutions. We're going to fill this in. What's our number of solutions here? But it's worth taking a look and remembering these terms that we used for systems of equations. We had the description. Intersecting, coincident, remember, means they are over the top of each other. Parallel means they never intersect. Consistent means there is at least one solution. Inconsistent means there is no solution. And independent and dependent are only relevant if there is a solution. And independent, remember, means they go their own way. Dependent means they're dependent on each other. They're following the exact same line. So how many solutions does this one have where it intersects in one spot? So that has one solution because it intersects in one spot. When they're coincident lines, this has infinitely many solutions. And when they're parallel lines, it has 0 solutions. We just went over those. All right, we also had a couple other methods for solving these equations. So one of these methods was substitution. And the key with substitution is we're trying to get a variable by itself so that we can plug it in. So you can see here this y value is by itself. And if we put a purple square around everything here that equals y, so y obviously equals itself, y equals itself, but this value also equals y, right? This equation tells us that. So this whole -x + 4 equals y. And we should be able to interchange any of these y values, right? So I'm going to take this value and put it in this little box right there. I get 2x plus 3. I leave a space for that box, equals 6. I take the stuff from the box and put it between the parentheses. Now all we need to do is solve. We're used to this, right? We're going to distribute. We get 2x plus negative 3x. So 3 times negative x is negative 3x. And then 3 times 4 is 12, equals 6. I'm going to combine my like terms here. 2x minus 3x is negative 1x. And we're getting x by itself, so I subtract 12 from both sides. I get negative x equals negative 6. Divide both sides by negative 1. And we get x equals 6. Nice. So are we done? Not quite. We're not quite done. Because we need an ordered pair, right? We need an x value and a y value. So now we need to take this value and plug it back in one of these original equations. So I'm going to take y equals negative x. I'm going to plug in my value of x here, plus 4. Now I can just simplify that. Negative 6 plus 4 equals negative 2. So my overall answer here is my 6 for my x, negative 2 for y. 6, negative 2 is my solution. Now we had a third method called elimination, and this one looks kind of intimidating because it has so many steps. But if you'll remember when we did elimination, it kind of quickly became one of our very favorite methods because when it worked, it was so easy. So let's take a look at that. Let's solve a couple of these by elimination. So how do we solve this by elimination? Let's see. Well, our method was to add straight down. So I'm going to add a to a here, and I get 2a. And now I have b, but adding that to negative b, those are going to cancel out, and I just get 0. Bring our equal sign down, and then 9 plus 1 is 10. So then I just get 2a equals 10, which is very simple to solve, right? We just get a equals 5. So that is an ideal case for solving by elimination. When we already have variables that are going to cancel each other out, it's easy to just add straight down and then solve for the other variable. We do need to go back now and find out what the other variable is. So I'm going to use this first equation, a plus b equals 9, plug in my value of a, subtract 5 from both sides, and I get b equals 4. So we can write this one as an ordered pair if we'd like. 5, 4. We could also write it as a equals 5, b equals 4. Any of those solutions will be valid. So give this one a try for elimination, solving this by elimination. Pause the video, see if you can do it on your own, see if you get the same answer I do. So we're going to add this straight down. The 3x and the negative 3x are going to cancel. 2y minus y, so 2 minus 1 is just going to be positive 1y. And then we add the 3's together. 3 plus 3 equals 6. So that's amazing. We didn't even have another step, right? Just the value of y completely fell out of the elimination process. So now we can go back and plug y back into one of these. I'm going to plug it back into this equation right here. So I get negative 3x minus value for y, which is 6, equals 3. Remember, I just got this from this equation right here. Negative 3x minus y equals 3. So now I can add 6 to both sides. That will go away. I get negative 3x equals 9. Divide both sides by negative 3. and I get x equals -3. Our solution here is -3, 6. So the key thing to remember in systems of equations is no matter what method you use, you should get the same answer. So really, you should use the method that makes the most sense. Look at the problem, and honestly, like most of the time, that answer might be graphing. Graphing is pretty easy as long as you can type the things in correctly. So go ahead and use graphing if it's an option. And you can always sketch a graph if you want to. But if Desmos is an option, use Desmos, use a graphing calculator. This is a great way to solve a system of linear equations. And you should always get the same answer. There are cases, though, where substitution and elimination look really optimal, really handy, right? If you have those given opposites in elimination, you're like really tempted to do it. Or if one of them is already solved from one of the variables, substitution starts to look like a really good option. So let's look at an example here where we didn't give you a method. You need to choose the method. What method would you use here, do you think? And if your answer is graphing, that's 100% okay. You can graph this. You just have to be really careful in Desmos because Desmos expects an x and a y value, and this uses P and Q. P and Q don't make sense to Desmos, so you need to change these to x and y values. You need to change that to x and that to y. And then you need to keep track of which one was which when you get your answer back. But I think there is actually an algebraic method that is really appealing here. Can you spot it? I think elimination makes a lot of sense here because these q's are going to cancel when we add the straight down. So if we use elimination, 3p minus 4p, so 3 minus 4 is -1p, equals 36 minus 67. Put that in my calculator, I get -31. Divide both sides by -1. Those negatives cancel, and I get p equals 31. Pretty easy. Now I put this into one of the original equations. 3 times p minus q equals 36. I put my value in for p. 3 times 31 is 93. I'm going to subtract 93 from both sides. I get negative q equals 36 minus 93 is -57. Now I'll just divide both sides by -1. Get rid of the negative. We get q equals 57. So our answer here, if we write it as an ordered pair, is 31, 57. Or we could just leave it as p equals 31, q equals 57. They didn't give us little softball, easy, tiny numbers that time, right? We had kind of bigger numbers. Now we can do this in Desmos as well. Let me pull up a browser. So here's Desmos. And if I want to type in these same equations, remember this was 3p minus q equals 36. I'm going to type them in exactly as it said. -4p plus q equals -67. And you can see here Desmos doesn't recognize those, it doesn't understand. So I'm going to need to change those to x and y, x and y. Now I can graph those, but you'll see here that you can't see anything on this chart. That's because these numbers are so big, we actually can't see the lines until we zoom way out. And then we can find where they intersect, maybe zoom back in there, figure out kind of where that is. 3157. So that's the exact same answer we just got, 3157. it was a little bit of a pain to do that, right? It's a little bit tricky. We had to change the x and the y, and we had to zoom out, we had to go all over. So that's kind of annoying to me sometimes. So you're welcome to use graphing, but sometimes it's annoying. Sometimes elimination might be the easier method. All right, our last piece here for reviewing Unit 2, or reviewing Unit 1, is word problems. Yes, we need to set up word problems, and then we solve them with one of those methods. So here's a word problem. Michael breeds chickens and ducks. Last month he sold 50 chickens and 30 ducks for $550. This month he sold 44 chickens and 36 ducks for $532. How much does a chicken cost and how much does a duck cost? And we're going to assume that the price of the chicken and the price of the duck did not change between these 2 months. It's the same price. Well, the first thing we need to do here is identify our variables and write them down. So you can look in the question. The question will usually, like the one with the question mark, the sentence with the question mark will usually tell you what your unknowns are. What are our unknowns here? How much does a chicken cost? Well, that sounds like one. How much does a chicken cost? We don't know that. And how much does a duck cost? We don't know that either. So maybe we'll call those variables C and D. Now we just read this original sentence and turn it into equations. So he sold 50 chickens and 30 ducks for $550. Well, the amount you get for selling a chicken is going to be the cost or the price of that chicken, which is our variable C. And then we multiply it by 50 chickens to get the total amount that he received. So it'll be 50 times C. Then we have 30 ducks, same idea, we'll add 30D. So this 50C is the amount he sold in chickens, and this is the amount he sold in ducks, in dollars. If we add those together, it says in the problem that this is $550. So 550 right there. Similarly, we can set up our second equation as 44C plus 36D equals 532. There's our system of equations. Actually kind of drew over it. There we go. Now we can use any one of our methods we want to solve this. Maybe we want to use Desmos again. That's totally fine. Graphing is a great way to solve linear equations. So once again, I'm going to have to type in x and y because our original equation was 50c plus 30d equals 550, and then 44c plus 36d equals 532. And Desmos doesn't understand c and d. We need to change that to x and y. Change this one to x and y. And I'm going to click the home button here in Desmos so I can get back to my original spot. And you can see right there is where they intersect at 8, 5. So this is the only tricky part of using Desmos, is I have to remember this one was what I said x was, and this one was what I said y was. Remember I said our answer was 8, 5, that's where they intersected. That's x, y, but I used x for c and y for d, which tells us chickens cost $8 and ducks cost $5. So that is how we set up a system of equations and solve it. So that is everything on today's objective. We are reviewing everything from Unit 1. Given a problem involving system of linear equations, I can choose a method and write the solution with 75% accuracy in 4 problems. Look at those little emojis and think about which one best represents you.